Hello everyone, my name is David Northcote and I will be presenting a few slides on gigahertz RF sampling for radio spectrum monitoring using the Xilinx RFSoC. So, we'll begin by reviewing spectrum management approaches, starting with the traditional fixed ways of allocating portions of the spectrum to users. Then we will review a recent development in the UK, which has been the introduction of shared spectrum licenses based on a user's location. Then we will consider dynamic spectrum access and consider the opportunities for this in the future. Finally, I will present a demonstration of the Xilinx RFSoC based prototype tool that combines the Ofcom UK frequency allocation table with an open source spectrum analyzer. This demonstration will showcase live spectrum monitoring with the RFSoC device. To give you an example of the fixed radio allocation method, the slide presents an excerpt of the Ofcom spectrum map for the whole of the UK. All of the given frequency bands in this chart are allocated for specific users and uses. This means that only users that are licensed for these particular bands can use them in the UK. However, there are exceptions such as the Wi-Fi band, which are unlicensed and free to use. To briefly explain how fixed spectrum allocation operates, this slide shows three bands allocated across the whole of the UK. Band 1, 2 and 3 can be used at any time by the license holder across a permanent or long-term basis. Alternatively, local license schemes are possible too, and to demonstrate this, a diagram of 4 areas in the UK that are labelled A, B, C and D are shown in the slide. Each of these areas are able to share frequency bands provided they are licensed in different geographical areas. For instance, Area A and C have attained a license for Band 1 without needing to allocate the band for the whole of the UK. Users can apply to Ofcom for a particular frequency band in their geographical area. This scheme is useful as it allows frequencies to be reused across the country and therefore makes better use of the spectrum. In the shared spectrum scheme, the shared users must coexist with the incumbent users, as the incumbent users already had licenses for the frequencies before shared spectrum was introduced. Cognitive radio is essential for managing the spectrum between the shared users and incumbent users. Techniques such as spectrum sensing can be useful to allow shared spectrum schemes to coexist with the incumbent users. As a vision for the future, shared spectrum can become more dynamic. Different users can obtain licenses to access the same spectrum in the same area as other users over time. In this slide, frequency band 1 in Area A contains different users accessing the same spectrum over time. In order to implement dynamic spectrum access, a smart radio is required that can access a spectrum management database and also perform spectrum monitoring. Therefore, with database information and observations of the radio spectrum, cognitive algorithms can be performed on the smart radio to make decisions on when to transmit on a particular frequency band and prevent interference. We're now going to review Xilinx radio frequency system on chip devices, better known as RFSoC. The RFSoC is a member of the Zinc system on chip family and is specifically targeted for RF applications. The device contains two primary components. These are the processing system and programmable logic. The processing system is host to the application and real-time processors, while the programmable logic contains Xilinx UltraScale Plus FPGA logic fabric. The programmable logic also contains unique RF resources known as data converters. These are two types of data converters, namely the RFADC and RFDAC. In 8x8 modes, the RFADCs can achieve a sample rate up to 4,096 megasamples per second, and the RFDACs can achieve a sample rate up to 6,554 megasamples per second. We can conceive embedded system development on Zinc devices as a stack of layers. Python Productivity on Zinc, better known as PINC, addresses the complexity of Zinc designs by providing a pre-configured stack of layers to support the developer. At the bottom of the stack is the hardware layer, which contains the FPGA bitstream and hardware accelerators. The software layer is in the middle of the stack and contains the operating system and existing Python software libraries that are immensely supported by the Python community. The top of the stack is the applications layer, where the user can interact with the system through Jupyter and IPython. So I just want to quickly review the open source spectrum analyzer design for RFSoC. This tool is entirely available from the user's web browser. The spectrum analyzer can achieve 2048 MHz of instantaneous bandwidth and can achieve an inspection range of 0 to 4096 MHz using the higher order nicrosome techniques. Fully supported Python software libraries are also used, such as Plotly and IPy widgets, to present the spectrum and create a dashboard for system control. So as you can see on the screen, a simple figure here is going to show you that the spectrum analyzer and the Ofcom database will give you the RF signals in the environment and exactly which band they belong to. In the demonstration, we will explore three main sectors: the broadcast sector, the public sector, and the mobile and wireless broadband sector. Lastly, it is important to state that the frequency spectrum is not being decoded or buffered in this demonstration, and so we're not breaking any rules or laws or regulations in this demo. So the spectrum analyzer is now shown on the screen. As you can see, the analyzer is displaying approximately 2 GHz of bandwidth. There are various control widgets on the right side of the analyzer, which control its center frequency and sample rate. Notably, the analyzer is also accessed using a web browser. There is an entry on the right hand side here for the spectrum map tool. Let's click on this and explore the different spectrum sectors that are available. By clicking the drop down menu, you can see that there are several entries here, for instance aeronautical, amateur, broadcasting, business radio. Let's click on the broadcasting sector for now, and this will reveal the bands. There are many, so let's focus on finding the FM radio band, which will be particularly visible in the spectrum. Clicking on the FM radio band entry will configure the spectrum analyzer to navigate to the FM radio band. As you can see, the FM radio band has now been identified and displayed in the spectrum analyzer plot. It's possible to see the power in the band from different FM radio stations across Glasgow. Hovering my mouse over the band displays a label that has correctly identified the band frequencies and name of the radio band. So let's now turn our attention to DAB radio. We can select the DAB radio band by clicking it from the spectrum map window. Doing so configures the spectrum analyzer to navigate to the DAB radio band. By decreasing the sample rate further using the widgets on the screen, you can quite clearly identify the DAB radio spectrum. Hovering over the band quite clearly shows the label that has correctly identified the band frequencies and the name of the radio band. Okay, let's now change the spectrum sector. Let's go instead now to the public sector. So here we can see quite clearly red bands on the screen that indicate the public sector frequencies. Let's now change the band of interest to around about 390 to 395 MHz. Okay, clicking on it reveals the band of interest, and you can quite clearly see that there's quite a lot of power there. As shown, quite a lot of activity, so let's just hover over it and make sure that the band has been displayed correctly and the frequencies have also been found. Now, finally, let's explore the mobile and wireless radio sector, which is always very interesting. Using the drop-down menu, we can click on mobile and wireless broadband. Let's look initially at the downlink spectrum access, around about 800 MHz, as there's quite a lot of power in this area. Let's click on the spectrum access downlink for Vodafone, for instance, and the spectrum analyzer will configure itself to navigate into that band. As you can see, we've identified some signals in the spectrum plot, and just hovering my mouse over the band of interest, we can see that we have found the Vodafone downlink band. Hovering next to the band that we selected in the spectrum map tool, you can see that the neighbouring bands have also been identified correctly too. Okay, lastly, to prove that this is all happening live, I have set up my phone to receive a video over my mobile service provider's network. I have placed my phone close to the spectrum analyzer antenna, and I would like to see if I can pick up any activity. For the purpose of this demo, I'm just going to move to the second channel of the RFSoC 2x2 board, because we do have two spectrum analyzers on here. Just look at the uplink, we can find that 1700 MHz is here. There we are. Okay, so switching on the spectrogram, you don't need to guess what mobile service provider I'm with. You could actually just hover over the band of interest, and what will be revealed is that I am with the Telefonica service provider. And you can quite clearly see activity in this band. Okay, now to conclude this presentation, we reviewed several spectrum management approaches. Then we introduced the Xilinx RFSoC based prototype, which uses the Ofcom spectrum map and an open source spectrum analyzer design for live spectrum monitoring. I hope you enjoyed this presentation and have a nice rest of your day.